That flash was over in a fraction of a second. It looks as if everything happened at the outlet. It did not. At that same instant, this circuit breaker launched a hidden sequencer race to stop enormous current before heat could turn one fault into a fire. So, what is actually happening inside? Start with the normal path. Current flows through the appliance and returns along the intended conductor. Now create a short circuit. 2 points at different voltages are joined by a very low impedance path. With far less resistance to hold it back, current can surge above its normal value. How high? That depends on the supply and wiring. But the danger is immediate. Conductors heat rapidly, connections are stressed, insulation can fail, and an arc or fire may follow. The breaker has to react fast. From the outside, a miniature circuit breaker looks like a simple resettable switch. Inside, it is watching for 2 different threats. A thermal element handles the slower problem, a sustained overload, but a short circuit demands a much faster response. For that, current passes directly through a coil, the magnetic trip. In milliseconds, that ordinary-looking coil becomes the trigger. Watch what the surge does. As current races through the coil, its magnetic field strengthens sharply. The field pulls a steel plunger, also called an armature, into the trip mechanism. That movement releases a latch. Here is the clever part. The plunger does not force the contacts apart. It unlocks energy already stored in a spring. The instant the latch lets go, the moving contact snaps away from the fixed contact. Fast, decisive, and still not the end. Opening the contact creates a gap, but current tries to keep flowing. Voltage across that widening gap can ionize the air into a conductive plasma channel, an electrical arc. Look closely. The contacts are open, yet current is still crossing the space between them. Left there, the arc's intense heat would erode the metal and let dangerous fault energy continue. So how does the breaker defeat something that can jump through air? It moves the arc. Geometry and magnetic forces drive it along an arc runner toward the chute. There, metal splitter plates take over. One concentrated arc becomes several shorter arcs. Each segment adds voltage drop. The plates absorb heat. The ionized gas cools, and the path becomes harder to sustain. But timing is crucial. In alternating current, current naturally crosses zero every half cycle. At that instant, the stretched and cooled arc has its best chance to die. If the gap cannot reignite, current does not return. The fault is finally interrupted, not when the contacts first move, but when the arc is extinguished. That rapid magnetic trip is built for a short circuit. An overload is different. A smaller excess current may persist without instant magnetic action. Instead, it heats a bimetal strip. As the strip bends, it releases the same latch more slowly. 2 threats, 2 timescales, thermal protection for sustained overloads, magnetic protection for violent fault current. After the trip, the contacts stay open. But remember what the breaker has and has not done. It protected the wiring. It did not repair the damaged appliance, cable, or outlet. The cause must be found before anyone resets it. Now replay the hidden chain. Current surges. The magnetic field pulls the plunger. The latch releases. Spring energy snaps the contacts open. The chute splits, cools, and extinguishes the arc. A violent fault begins in an instant. Inside the breaker, a precisely timed mechanical race brings it to a safe stop.